All right, welcome back. So in the previous example, we looked at differentiating the geometric series to get a new result, and that was that this series of 1 for 1 over 1 minus x quantity squared is actually this infinite series, and it converges as long as the absolute value of x is less than 1. So now we want to turn around and go the other way, and we want to integrate this series. We want to integrate this series to create a new power series. So first, let's deal with the integral of this thing. So since it's 1 over that stuff and there's nothing better to do, we'll let u be 1 minus x, and du will be minus 1 dx. So we make those adjustments. Put the negative out front. 1 over 1 minus x, and then we'll have our minus 1 dx. There you get the negative going out front to account for that. So this is going to be a 1 over u integral. Integral of 1 over u is ln. So that negative will carry through. ln, absolute value of 1 minus x. Absolute value of 1 minus x. Okay. Okay. And now the original interval of convergence was absolute value of x less than 1. If absolute value of x is less than 1, that means that x is between 1 and minus 1. So if x is falling between 1 and minus 1, in other words, x is smaller than 1, then ln, stuff inside the ln, 1 minus x, is always positive. So we can actually drop this absolute value and just have negative ln of parentheses 1 minus x. So we can actually drop the absolute value, right? Because this is going to be converging only when absolute value of x is less than 1. And so therefore we have negative ln of 1 minus x. Negative ln of 1 minus x. Okay? So that's what the integral is. What's the series going to be? Well, let's do the integral of the series. Let's do the integral of the series. So, in other words, integral of the series x to the k dx, again, as k is going from 0, right? K is going from 0 to infinity. So remember, the terms of our thing look like this: 1 plus x squared plus x cubed, and so on. So applying the power rule piece by piece, we would have x to the k plus 1 divided by k plus 1. That would be inside of our series. So the terms would look like this: x plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4, and so on forever. Right? Now, keep in mind here now that the 0 term that was originally there, this is still going from 0. We didn't lose anything with 0. All right, 0 is okay because that worked. Right, the 1 becomes an x to the first. So we're okay here. So we have the sum as k goes from 0 to infinity now. Unlike with the derivative one, where we had to rearrange it and then make an adjustment to our coefficients, that's not the case here. Everything's actually okay, so we're still stuck on k equals 0 to infinity. There's one thing that's missing. These were integrals, definite or indefinite integrals, so there is a plus a constant laying off to the side here. So at this point we have this result. Negative ln of 1 minus x is equal to the sum x to the k plus 1 over k plus 1 plus a constant c. And that constant c hanging in there. So we need to actually evaluate this for a particular value. So we need to figure out what c is. But fortunately, we can very easily by just saying let x be 0. If I plug 0 in there, I'm going to have negative ln of 1 minus 0 equals 0 plus c. But ln of 1 is 0. So you're going to have 0 equals 0 plus c. So it turns out in this case the constant of integration is 0. So we now finally have this result. Minus ln of 1 minus x is equal to the series. Now that's x going from 0 to infinity. I'm going to make one small adjustment to that, and I'm going to start the sum at 1, so I'm actually going to shift it up 1. And this is just because this is traditionally what it is. There's nothing wrong with saying sum is 0 as you go from 0 to infinity of x to the k plus 1 over k plus 1, but it's traditionally written this way. Okay, it's traditionally written this way. And so then there's just one final little adjustment that we need to make, and that is that bring the negative over. So ln of 1 minus x is the negative of the series. K goes from 1 to infinity of x to the k over k, which actually looks like this series here. Expanded out, it would look like this. Minus x squared over 2 minus x cubed over 3, and so on. Okay. And so we have this infinite series. Okay. So one quick thing, again, this will converge on the interval minus 1 to 1, right? So we know that will converge on the interval minus 1 to 1. Okay. So an interesting thing happens here. Real quick. Quick little note. If we let x be negative 1 in this series, let x be negative 1, then on the left-hand side of this equation, you would have ln of 1 minus negative 1 would be ln of 2. Okay. On the other side, if we let x be negative 1, we would have negative 1 times the sum of minus 1 to the k over k. K goes from 1 to infinity. I can actually just absorb that minus 1 into the sum. And that would actually make the sum be minus 1 to the k plus 1 over k, as k goes from 1 to infinity. And what would that series be? What would that series be when we put on that minus 1? That would be 1 minus 1/2 plus 1/3 plus minus 1/4. In other words, this is the alternating harmonic series. Unfortunately, at this point in time, we cannot say we do know that the alternating harmonic series converges. We do know that it converges. But we can't right now say that it converges to ln of 2 because our result only guarantees convergence. This result that we have only guarantees that it works if we're inside the endpoints. It turns out in this case, the alternating harmonic series actually does converge to ln of 2, but we're not able to actually state that yet. Right? We can't actually find that result yet, but it turns out it will actually converge to ln of 2. And this is kind of a reason why you might suspect that it does. We know it converges, so we suspect that it would converge to ln of 2. Since if we plug -1 into the original function, it does give us ln of 2. And it actually turns out it does. But we can't say that with our result from the integral. And we can't do that simply because the result only guarantees this result, that the integral converges to the integral of the pieces for the internal points only. So that's why we can't say it yet. But it turns out it actually is the case. And so that's kind of a neat little thing that the alternating harmonic series actually comes out from a power series for the logarithm. It's kind of a cool, neat little thing there.